Hi, I'm Randall Heyman. This is my 154th coronavirus video. If you'd like me to make a video for you for free, then contact me by email or commenting below any of my videos. Okay, so I'm going to do a video for Balthazar. He asked me to do something on the first isomorphism theorem for groups with a real example. So I'm happy to do that. So let's start, I think, by just writing up what it is, what the theorem is. And here I'm just going to use straight out of the book Freilich on algebra. So let's go, let phi, which goes from a group G to G dash, another group, be a homomorphism with kernel K. Okay, let's just stop right there and we'll just talk about this. So you're thinking here, here's G and here's G dash, and we've got some function here, phi, and this is a homomorphism, a group homomorphism. And what that means is that if you take phi, say A plus B, plus is the group action or operation that we're using here, just equals phi of A plus phi of B. That's all that means. So it doesn't matter whether you add two things in here first and then apply this function, or you apply the function to each of the elements A and B and then you add them up once you get over to here. And the kernel K, kernel's often also referred to as null space. So the kernel K is just the elements that phi sends to 0. So K, it'll just equal the set G, they're in the group G, such that phi of G, little g, equals 0, whatever the 0 element is in the group. Okay, so I'll go on. Let this be, what's this going to be? Okay, in fact, I'm just going to make it, let's just make it that, makes it a bit easier. So gamma is, it's going to go from G to G quotiented out by K. I don't know, B. And here they're calling it the canonical, which you might also think of as just the natural, the obvious homomorphism. Okay. Now, if you don't know this bit here, the quotient group, then have a look at my video. I've got videos I've done in the last few months on all of this stuff, homomorphisms, groups, and quotient groups or factor groups. Okay, so that's that. And then the conclusion is there is a unique isomorphism. Remember, isomorphism just means that the two things are identical. It's just subject to doing some relabeling. That's basically what it means. And it's mu, and it's going to be from G quotiented out by K to phi phi of G. And phi of G in this sense, that just means that that's essentially the range of phi, such that phi of X equals mu of gamma X for all X in G. Okay, so let's draw a diagram that sort of explains how this works. And what I'll probably do is first put the general thing, and then we'll put a specific example. So here we've got G, and here we've got phi of G, and we'll put a little arrow this way, and we'll call it, this is the function phi. And now we want to go from here down to about there, and we'll put down here G of K, sorry, G quotiented out by K, and this will be gamma. And we'll put the little arrow, goes that way. And then we've got the isomorphism to put in. So let's draw that in. So I'll go from there. That's not very good, is it? Let's go from there to there. That's better. So let me just do a bit of patching up here. So I'll actually put this with arrows both ways. But, well, actually, no, I won't, because we need to notate going this way. So let's call this one mu, but it is an isomorphism. So what this is saying from that very last bit, it's saying that we can go from here, start here, and we can go this way to get to here. But the other way, all it's saying is the other way we can go is we can go down here to this and then go up here, and we'll get to the same result. Okay. So now let's do a little example. Okay, so let's get rid of G. Let's get rid of that. I'll get rid of that. Maybe, I don't know. Let's see. Let's call this ZX. Actually, let's use a different color so that it's very clear that we're now talking about an example, ZX. And what is ZX? It's the set of A0, it's a set of polynomials with integer coefficients, A1, X plus dot, 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 A, say little m, X to the m, where all the A's are integers and m is greater than or equal to 0. So these are just the polynomials. Example, let's use as our little polynomial today, x squared plus 7. That is an element of ZX. Okay, so what's this phi going to do? So phi in this case, so let's draw here, we'll still call it phi. But what does phi actually do? Well, it takes a polynomial p, that's one of these polynomials in ZX, and it turns it into p evaluated at 0. So what are we going to have here? We're going to have a set. Now, if we go back here, you can see the polynomial, this one here. If we evaluate that at 0, we get 7. We could have the polynomial, let's draw a few up here. X squared plus 7. When we apply phi, we get 7. X cubed plus x minus 2, we get minus 2. Okay, so what are we going to have? What are we going to have here? What are all the possible values that we could have here? Well, it's just it's basically all the integers: -1, 0, 1, 2, dot, dot, dot. So if you like, it's just z. Okay. Now, what's the kernel? Let's talk about the kernel here in, say, green. The kernel of phi. Well, remember, the kernel is all the things that get sent to 0 by phi. So it'll be the set of it's a set of P such that P is an element of ZX. So it's one of these polynomials. with integer coefficients, and P of well, it's all the ones that have 0 coefficients, isn't it? Because I'll put some examples in a sec, but it P with A0 equals 0. So that A0 I'm talking about, we can see back here. So examples. So these are just all the polynomials that don't have, that have a 0 constant coefficient. So x squared, 7x cubed plus x squared plus 5x. All of these x, all of these are in the kernel of phi. Okay, so now let's direct our attention to here. So we have to quotient out, that's right, push this up. We've got to quotient out zx by the kernel. So I'll actually rewrite this now. We know what it is. Well, we know the notation for what it is. It's that slash the kernel of that. Now, I've done a video on quotient groups. There is a proper formula for it, but one way that you can often think about it is my alien conversation. Imagine you were trying to explain to an alien this, the integer polynomials, and this alien's very funny because in his world, he understands the kernel. He understands all of these perfectly, but he doesn't understand ZX. So what you would end up saying to him is, what would you end up? You would end up saying to him, well, there's all these, essentially you would say there's polynomials where P of 0 equals, say, 5. Actually, that's probably not the best way to explain it. Well, let me just write out what it is first. Yeah, what you would say to him is this. You'd say, look, there's a whole group of polynomials that have a constant coefficient of -2. And then there's some with -1, there's some with the 0. 0 is, of course, that kernel one. And then 1, and then 2, whoops, and then on it would go. So this one here is actually, it's all the polynomials. P is an integer coefficient, and P of 0 equals -2. Or you could say A0 equals -2. So you group them all together. That's how you would say to the alien, look, you understand the situation with coefficients with 0. In fact, it's a lot richer than that. There's all these other polynomials that have different constant coefficients. Okay, so that's good. And what does the isomorphism theorem tell us? It tells us that there's some isomorphism mu between this set and this set. And I think you can see it's pretty obvious what that isomorphism theorem is. So let's write it out. Mu goes from the integers quotiented out by the kernel of phi, and it goes in the case of going this way, it goes to z. And what does it say? It basically says, look, if you've got if you've got an equivalence class here, let's call it J, well, then it's just going to become J. That's all it's saying. That's all it's saying. Okay, so that's the first isomorphism theorem. If you have questions about this quotient group or factor group, please have a look at my video where I go through it in a bit more detail. But most people who get to this stage are starting to get comfortable with how that works. Okay, so that's all for the first isomorphism theorem. I hope Balthazar and anyone else watching has found it useful.